Hi everyone. In the previous lecture, we spoke about the non-inverting RC integrator, the step response of a non-inverting RC integrator. To continue that lecture, we'll now talk about the step response of an RL integrator. This is an ideal RL non-inverting integrator. It's given that the resistance value is 1 kilo ohm and the time constant L upon R is 1 millisecond. And again, the op amp is ideal except for the saturating voltages. That is, the op amp's output cannot go greater than plus minus 15. I mean, it has to, it can only take values between plus and minus 15. Okay, that is, the op amp has a saturating nonlinear characteristics where the maximum value it can reach is plus 15 and minimum is minus 15. And it's also given the initial condition. If you guys recall, I said that when we started off the discussion, we said we need to know the initial conditions, especially when the circuits happens to be ideal integrators. Okay, but because there is no DC steady state feedback, so you can't precisely define the output voltages. So to define the voltages precisely, you need to know the initial conditions of the circuit. Okay, either initial current of the resistor, or in case of an RC integrator, you need to know the initial voltage across the capacitor. So here IL of 0 minus is the initial current, and we have to analyze it for two cases. IL of 0 minus is 0 and 5 milliampere. So we have to do the same exercise. We'll have to find out what is the output voltage for all time, what is the inverting node voltage, which happens to be the virtual node for all time, and also what happens to be the inductor current. So the direction of current is shown here in this way, IL of t for all time. So first, if you start with the analysis for t less than 0 or t equal to 0 minus. So for t equal to 0 minus, this circuit, if you see, the input has not arrived at, so this node is at ground, and the output node voltage is simply given by this node will also be, because in the steady state inductor will act like a short circuit, so therefore Vx, this node will come to 0. So Vx of 0 minus is 0, and the inverting terminal, non-inverting terminal is also at 0 volts. The differential input to the op amp is 0, and we said even though the differential input is 0, for an ideal op amp with the saturating characteristics, the voltage can be anywhere between minus 15 to plus 15. Okay, we already said that. And the voltage, you need to know the initial condition of in the circuit. So here it is given IL of 0 minus is given to be the initial current flowing through the inductor. So the output voltage will simply be equal to, your V naught of 0 minus will simply be IL of 0 minus times R. If you assume IL of 0 minus is 0, then that will be simply equal to 0 volts. Okay, so now you know all the three parameters. IL of 0 minus is known, that's given to you. That will be your inductor current at t less than 0, and the output voltage is also known in terms of the inductor current and the resistor. Now comes the switching event. Suddenly at t equal to 0, a step input is applied to the circuit. The moment a step input is applied, what will an inductor do? An inductor, if you recall from the last lectures, we said will suddenly, the current through an inductor cannot change instantaneously. Okay, which means it will just act like an ideal current source of value IL of 0 minus at t equal to 0. When the step appears, you can just replace the inductor with a current source. Now you are reduced with a very simple circuit like this. You have an op amp circuit with some resistor in the feedback and a constant current source. So if I incrementally find out what is the feedback factor, that will be equal to 1. If I change this node by delta V, this node will also change by the same amount, right? For the incremental impedance of an ideal current source is infinity. So I can, incrementally, if I represent this model, this node will also change by delta V. So the feedback factor is unity in this circuit. Okay, this is for small signal. Mind you, this is a small signal. You will also have to add the DC bias on top of it if you want to do an exact analysis and find the output voltage. Okay, so the most important thing here is that the moment I say there is negative feedback, we know from our basic analysis that V plus equals V minus. basic op-amp analysis, we know V plus, so this node voltage will immediately come to 10 volts. Okay, so now the output node voltage is simply given by IL 0 minus R is the voltage across the resistor plus this node voltage plus 10 volts. So your output voltage will suddenly jump. It initially started off as IL 0 minus times R, and then it will suddenly jump by an extra 10 volts at t equal to 0. So remember, the voltage across an inductor can change instantaneously. It's the current that cannot change instantaneously. So the voltage across the inductor, which is Vx of t, which is also the inverting terminal voltage, also suddenly jumps from, it was initially at 0 and it jumps to 10 volts. Okay, and the inductor current was initially at IL 0 minus, and that will stay constant as IL 0 minus even at even at t equal to 0 plus, it will be IL 0 minus. So IL of 0 plus will also be equal to IL of 0 minus. Okay, this follows from the inductor current not being, the inductor current not changing instantaneously. For the inductor current to change instantaneously, you need to apply an impulse of voltage across it. Even a sudden step will not help. You have to apply a sudden impulse of voltage. Only then you will see a sudden step changes in currents. Okay, since we are applying a finite voltage, in the circuit, if you see, there is only a finite change across the inductor's voltage. It's a 10 volt step change. So that won't increase the current abruptly. Okay, so now we have drawn for t equal to 0 plus. The output voltage jumps by 10 volts. It starts off at IL 0 minus times R and jumps to 10 volts. Okay, plus 10 volts. So if you assume the initial inductor current is 0, then the output voltage will jump from 0 to 10 volts. If you assume the initial inductor current to be 5 milliamperes, then 5 milliamperes times 1 kilo ohm is 5 volts. It will jump from 5 volts to 15 volts. So initially we will assume 0. So the output voltage goes from 0 to 10 volts. Now what happens for t greater than 0? So for t greater than 0, we just saw that the circuit just enters a negative feedback mode. So the standard analysis holds. So this will act like a non-inverting integrator with a proportional term. So the output voltage is given by this. The output voltage is simply Vi plus R by L, which I will write it as 1 by tau times Vi dt, plus I should also remember, whenever I am writing this, I should also write the initial condition. Because there is an integral term, I should write the initial condition. If the initial condition is 0, I can ignore the integral, I can ignore this term. Okay, so now if you want to find the output voltage, it starts off at 10. I am assuming the initial inductor current to be 0, so it will start off at 10. Now if you see, the inductor voltage is 10 volts. There is a proper 10 volt appearing across the inductor. So this voltage sets off a current, and the current flowing through the inductor is given by 1 by integral 10 times dt. So it's going to increase, because there is a constant voltage, the inductor current will increase linearly. Remember, all the while this node voltage is stuck at 10 volts. It's always staying at 10. The inductor current is increasing linearly, which means the voltage across the resistor, which is simply the inductor current times the resistor, will also increase linearly. So it's just an integration operation. That's what we are capturing here. Okay, so the voltage across the resistor will increase linearly. That is simply, the output voltage is simply what? Voltage across the resistor plus 10 volts. So it is 10, it starts off at 10 and starts increasing linearly with a slope of 10 by tau. Okay, 10 by tau volt per seconds. So if you assume tau as 1 millisecond, it increases at a rate of 10 volt per millisecond. So if we are assuming IL of 0 minus is 0, so the output voltage jumps to 10 volts, and from then onwards it starts increasing linearly with a slope of 10 volt per millisecond. So within half a millisecond it will reach 15 volts. Okay, so if you substitute t equals tau by 2, which is half a millisecond, you will get V0 will become equal to 15 volts. At that point, the circuit will enter the open loop mode. right? Because after that your output cannot increase, it will enter the open loop mode. So what happens to the inductor current? If you are to plot the inductor current, the current flowing through the inductor, either I can integrate and find out the current. I know it's increasing linearly. Why? Because the current through the voltage across the inductor is constant, so it is increasing linearly with time. So I know the initial value, which is 0. How do I find the final value of the current? I mean, when I say final value, I'm talking about the value at t equals tau by 2. How do I find that? I know the voltage across the resistor. What is that? That is simply V0 minus Vx. V0 is 15 volts and Vx is 10 volts divided by R, I get 5 milliampere. So the inductor current increases to 5 milliamperes at t equal to tau by 2 seconds. The node voltage Vx remains constant. It was initially 0. When the step event happened, it jumped to 10 volts and it is remaining constant at 10 volts till tau by 2 seconds. Now once you reach tau by 2 seconds, after that the circuit will enter open loop mode, because your op-amp's output cannot change anymore. The op-amp's output cannot change anymore, it cannot increase anymore. We say that the delta V0, the incremental change in the op-amp's output voltage, becomes 0 from that point onwards. For t greater than tau by 2, the incremental change in the op-amp's output is 0. So therefore, the op-amp, we can say the forward path gain of the op-amp becomes 0, which means there is no loop gain, so therefore there is no feedback. So I can simply ignore this op-amp and simply model it as a DC voltage source of value 15 volts. So, okay, so now we have this representation. You have the circuit reduces to, because there is no op-amp, you just have a resistor and inductor in series, the circuit reduces to an RL circuit. So 15 volt is the one terminal of the resistor, the other terminal of the resistor is connected to the inductor. The voltage across the inductor is currently 10. So this circuit is valid for t greater than tau by 2 seconds. The initial voltage across the inductor is 10 and the current flowing through the circuit we just calculated at t equal to tau by 2 seconds is 5 milliampere. So whenever you have an RL circuit, what happens in the steady state? In the steady state, the inductor will act like a short circuit. So there will be no current, there will be no voltage drop across the resistor. And it will be carrying some constant DC current. So the voltage across the inductor will go down to 0, we know that. So that is simply Vx, right? So Vx started off at 0, suddenly jumped to 10 volts, remained at 10 volts till tau by 2 seconds. After that, it decays down to 0. With the time constant given by L by R, which is 1 millisecond. And what happens to the inductor current? The inductor current was initially 0. It was IL of 0 minus, which is 0. Then it was slowly ramping up, increasing, and it peaked to a value of 5 milliampere at t equal to tau by 2 seconds. From that point onwards, the inductor current, because it's an RL circuit, eventually when the voltage across the inductor comes to 0 volts, the current flowing through the resistor is simply given by 15 by R. So from 5 milliampere, it reaches a value of 15 by R, which is 15 milliamperes. It starts off at 5 and gradually increases to 15 milliampere with a time constant of L by R, which is again 1 millisecond. Okay, so that's what happens in this circuit. So the inductor current, first it's a linear increase till 5 milli. After that, it's an exponential first order increase to 15 milliamperes. So if you assume most of the current, most of the cycling happens within 5 time constants, it will take, if you start off, this is 0, 0.5 milliseconds it reached 5 milliampere and an additional 5 time constants, an additional 5 milliseconds. So total duration will be, in 5.5 milliseconds it would have reached 15 milliamperes. Okay, so this is 5 time constants. We are assuming within 5 time constants it had more or less settled to its final value. Right? So anytime you are given a first order circuit, it's pretty simple. If you know the initial value and final value, you can draw the waveforms. So Vx starts off at 0, jumps to 10, and then from then onwards it remains constant till tau by 2 seconds, and then onwards it drops to 0. V0, what will happen to V0? it reached 15, okay, V0, the output voltage V0 suddenly jumped to 10 volts at t equal to 0. Then it underwent a linear increase, reached 15 volts, and it remained constant after that. So remember, just for verification, for the output to remain constant at 15 volts, the input differential voltage should be always greater than 0. So you should check if it is guaranteed or not. What is V plus? V plus is at 10 volts. What is V minus? V minus, the maximum value was at 10, and after that it is always decaying. It's always less than 10. Eventually it goes to 0. V minus goes to 0 eventually. So Vd is always greater than 0, and in the steady state Vd becomes 10 volts. So which means since Vd is always greater than 0, I can say output voltage will always stay put at 15 volts. So now we have plotted the inductor current, the inverting terminal voltage, and the output voltage as well. Now to draw it for a different initial condition, what happens if your IL of 0 minus happens to be 5 milliampere? It's a very trivial exercise. You can directly analyze it here itself. If you see the op-amp's initial current, I'll probably show it on a different slide, I'm sorry. So if you look at this circuit, so if you are to analyze the circuit, and it's given the initial current flowing through the inductor is 5 milliamperes, and the resistance value is 1 kilo ohm. So before t equal to 0, we can assume this is at ground, and it's carrying a 5 milliampere current with 0 volts across it, steady state, so 0 volts, and resistance is also carrying the same 5 milli, so the output voltage will start off at 5 volts. The instant a step input is applied of 10 volt magnitude, 0 to 10 volts, the node Vx will increase to 10 volts, and the output voltage was initially, it was already, to begin with, it was at 5 volts. It will jump by another 10 volts and reach 15 volts. So at t equal to 0 plus itself, the output starts to saturate. And what happens to inductor current? It has always been 5 milliamperes to begin with, and it stays at 5 milliampere even at t equal to 0 plus. So the inductor current is at 5 milli, and then it stays at the same 5 milliampere after the step has arrived as well. From then onwards, once the op-amp enters the open loop mode, we just saw that the op-amp, you can replace it with a 15 volt DC source, and the eventual voltage, this is Vx is the voltage across the inductor, it will become a first order RL circuit. It will decay down to 0. The output voltage will stay put at 15, and the inductor current will increase have an exponential rise to a peak value of 15 milliamperes. Okay, so the change in the waveform shape occurs because of where we started off. So it matters. If your initial condition is different, then the waveforms will also look very different. So you can, as an exercise, try it out. What happens if your initial current is minus 5 milliamperes? Okay, your output voltage will start off at minus 5 volts. It will start at minus 5, and then at t equal to 0, it will have a jump of 10 volts. So it will go to plus 5 volts, and from there it will increase linearly with a slope of 10 volt per millisecond. So 10 volt per millisecond slope, it will increase with a slope of 10 volts per millisecond. So if you are at 5 volts, to reach 15 volts, the output voltage has to change by 10 volts. And that change in 10 volts will happen in a millisecond. So in 1 millisecond, it will reach the peak value. Similarly, the current will start off at minus 5. It will stay at minus 5. And then it will slowly increase. When the output reaches it will start off at minus 5 milliamperes. When the output reaches 1 millisecond, it will reach a value of 5 milliamperes. Okay, the peak value will remain the same, because why is that? If you guys recall, the op-amp, the resistor, the current matters, the value of the current is given by the current through the resistor. At this point, when the output voltage reaches 15, the inverting terminal is at 10, So the current flowing through the resistor is plus 5 milliamperes. So the polarity of the current changes from minus 5 to plus 5. Okay, somewhere in between it goes to 0. I think at half a millisecond it goes to 0. And then it builds an additional 5 milliamperes of current. After that, the op-amp will enter open loop, and the node voltage Vx, we were drawing the node voltage, I have not shown the node voltage Vx here, but you can draw it yourself. The node voltage Vx will start off at 0, it will jump to 10 volts, it will remain constant for 1 millisecond, and after that it will decay down to 0. And output voltage will stay put at 15 volts, and the inductor current, the current through the inductor will start off at 15, 5 milli, and eventually reach 15 milliamperes. Okay, so that again follows directly from this. Eventually the inductor will act like a short circuit, and this node voltage is at 10. Inductor will act like a short circuit, so this node will come to 0 volts here. Output is at 15, so the total current flowing through the inductor will be 15 minus 0 by R, which is 15 milliamperes. So it will start off at 5 milli, the op-amp will enter open loop, and then it will exponentially charge to 15 milliamperes in the steady state with a time constant of 1 millisecond. So if I ask you what is the total time for the inductor current to settle down, starting at t equal to 0, it will be 1 millisecond, it will charge linearly, and for 5 milliseconds, so I'm assuming 5 time constant settling, so for 5 milliseconds it will charge exponentially. So for the current to reach from minus 5 milliamperes to plus 15 milliamperes, the total time it takes is 6 milliseconds, approximately 6 milliseconds. Okay, so that's it about this non-inverting RL integrator. We'll solve a few more problems, some very interesting problems in the upcoming lectures, and then I'll hopefully close off this transient response of integrators in a few more lectures. Thank you.